Which of these three objects do you think you would be able to throw the furthest? A Rubik's Cube, a baseball, or a Frisbee? To find out the answer and explain, let's use science.
Science!
Hello everyone. In this video, I'm going to show you how we can use science, specifically Newton's third law of motion, which is a great model for the basic principles of flight, and we're also going to be taking a look at the Bernoulli Principle to explain exactly why is it that we can throw some objects much further in the air than we can throw other objects. If you need a quick refresher on the basic principles of flight, I actually have a little key up here in the upper right-hand corner of the screen. And as I said before, the 4 basic principles of flight are a very good model of Newton's third law. Newton's third law states that for each and every action, there is an equal and opposite reaction. So if we look at these 4 forces right here, let's just see what's going on. So the force of weight is pulling downward towards Earth. Weight can be loosely defined as mass times gravity. The force of gravity is going to remain consistent in this hypothetical experiment for us because we're going to assume that we're throwing all 3 of these objects on Earth at sea level. So the force of gravity is going to remain the same. The equal and opposite force counterbalancing weight is what's known as lift, and lift can be loosely defined as air movement. Air movement is going to be explained by the Bernoulli Principle. The Bernoulli Principle is what explains lift by a difference in air pressure. So if you have an object with a high amount of air pressure and a low amount of air pressure, that low amount of air pressure actually pushes the object up into the air. Okay, conversely, on the other side of things here, we have thrust and drag. Drag can be loosely defined as air resistance, and that's going to be variable between these objects based on their shape and their design. An object like a cube is going to have very, very high drag because it's not going to cut through the air. Whereas an object like a Frisbee right here, you see the cross-section of it, it's very sharp, it's going to have very low drag, and it's going to cut through the air like a knife. Okay, so for this specific experiment, we're going to go ahead and say that weight is not going to be a factor in what's causing these 3 objects to fly different distances. Because you'll see here that I am going to make the assumption that all of these objects have the same mass. We've already stated that we're going to throw these objects on Earth at sea level, so the gravity is going to be the same. Yeah, I hear you saying, okay, there's going to be some variance in maybe different brands of Rubik's Cubes. Major League Baseball actually defines that there's a 7-gram variance between 142 and 149 grams for an average baseball. So 2 baseballs from the same game can have different weights. And Frisbees, there are tons of different shapes, sizes, styles, designs, models, and obviously masses of Frisbees. But for this experiment, let's just go ahead and assume the masses are the same across the board. So weight is not going to be a factor. Also, I'm going to go ahead and say thrust is not going to be a factor because for this hypothetical experiment, I'm going to say that we're going to have one person supply the same amount of thrust to each of these objects. That could be just an average person off the street, and we say, we want you to throw this Rubik's Cube, this baseball, and this Frisbee. It could be Aroldis Chapman, the fastest pitcher in Major League Baseball, who throws a 105-mile-an-hour fastball. Either way, we're going to assume the thrust put into each of these objects is the same. So what does that leave? Well, these objects do have a great degree of difference in their drag and in their lift. And let's go ahead and explain that. So the Rubik's Cube is going to have the highest amount of drag and the lowest amount of lift. This is because of its shape. It has a very high coefficient of drag. Just the cube shape, any shape that is big and boxy and angular is not designed to cut through the wind. The air is going to be coming in, it's going to be pushed off in all different directions due to the faces of this object, and you can actually find pictures and videos online of people putting really angular shaped things like cubes in an aerodynamic simulation, and the air pocket behind is just a mess. All in all, this does not create a very aerodynamic shape. So I actually don't know what the world record is to throw a Rubik's Cube. I'm going to say that it's probably less than 125 meters. which is approximately equal to 410 feet. And the reason I say that with confidence is because a baseball, the world record for throwing a baseball is 136 meters, which is about the equivalent of 445 feet. Canadian pitcher Glenn Gorbis achieved this feat in 1959, and his record still stands today. Now, why is this the case? Well, a baseball has a medium amount of drag in comparison to the Rubiks Cube, and it has a medium amount of lift. That's because when a baseball is thrown, the air moves both around the baseball on the top and the bottom. The stitches actually come into play. They reduce the amount of drag on the baseball as if it were just a plain sphere with no stitches, and they create a little bit of lift because the baseball is spinning, and that creates some rotation in the stitches also, and that creates a little bit of lift. So we have more lift, we have less drag, and that's what allows the baseball to stay in the air longer and travel at a higher speed. Therefore, more distance. However, you can probably see where I'm going with this. And the Frisbee is going to have the least amount of drag and the highest amount of lift. And what that does is that creates a world record Frisbee throw of an amazing 338 meters, which is the equivalent of over 1,100 feet, 1,108 feet to be exact. So to give you some perspective, if you can imagine a football field, 3 of them actually to be exact, and you have a person throwing that Frisbee, the Frisbee would go over all 3 football fields. The baseball would go over 1 and stop somewhere about right here. And the Rubiks Cube, you're lucky if it's getting over the first football field. So you see, just in perspective, the differences in these types of distances. Now, let's go back and revisit this factor of the Bernoulli Principle, because that's what's creating the high amount of lift in the design of the Frisbee. And we can really see that and really appreciate it when we look at the cross-section of Frisbee right here. So in the Bernoulli Principle, we're going to be talking about 2 specific things and how they relate to each other. We've got air speed, and we've got air pressure. So if we stick to green for the Frisbee here. So underneath, there is a very, very low airspeed. That low airspeed creates a high amount of air pressure, and that is what causes the lift and keeps the Frisbee aloft. Conversely, the top of the Frisbee is curved, so the air traveling across is going much, much faster. That's creating a little amount of downward force, but not nearly the same. So that means that the airspeed is very high, and that results in a very low pocket of air pressure. So you see, because of the Bernoulli Principle, the Frisbee has the highest amount of lift. Because the Frisbee has the highest amount of lift, it stays in the air the longest. Because the Frisbee has the least amount of drag in the airfoil-like design, it cuts through the air. That allows it to travel the fastest while staying in the air the longest. As a result, the Frisbee is going to be able to be thrown the furthest nearly every time. I hope that you've learned something from this video and that you've at least been able to explain with hard scientific facts why it is that we can throw Frisbees much, much further than we can throw baseballs and Rubik's Cubes, even though they all weigh the same amount. Now that you've learned this great bit of science, please go home and teach your parents and educate your friends about it, and tune in next time to learn something else.
Science!